Hi there. Got a couple of questions to go over that it's probably just easier to do as a video rather than over there. So I've been asked to do these by Ayla. This is kind of like maths karaoke, the best type of karaoke, but I'm going to go over basically an optimization question here and a log question as well. Okay, now actually these are two of the toughest questions, one of the toughest optimization questions I've seen and one of the toughest log questions I've seen, so they maybe were worthwhile going over before the exam. Okay, now here we've got two graphs or a rectangle sitting between two graphs where Q and R are on the upper parabola. S and P are parallel across T, parallel to RQ, and passes through T, and they're both parallel to the x-axis, which is important. Okay, so in part A, TP is equal to x units, and we want to find an expression for the length of PQ. So we know in here, okay, from this point to this point is x, and we're looking for an expression for PQ, for the length of PQ. Okay, now the key point here is that Q there lies on that curve here, which is y equals 10 minus x squared. T as well and P, because that line S to P is parallel to the x-axis, these two things have the same height. Okay, so because Q's up here, we know the height of Q, or we know expression for the height of Q because it lies exactly on that top curve. And we can also figure out the height of P because it's the same height as T. Okay, so the y coordinate of T and P, well, T is on the y-axis. So for T, x is 0. Okay, so at T, x is equal to 0. And we know that it's y is equal to 2/5 of 10 minus x squared for that point T. Sorry, I just messed up with my pen. Okay, so T is x is 0, so y is going to be 2/5 10 minus 0 squared. So that's just 10, so 2/5 of 10 is 4. So that distance there is 4. Okay, which means it's exactly the same there. Now the y coordinate of Q, well, we don't know exactly what it is, but because that distance there from T to P is x, that Q is going to be the y coordinate when the x coordinate is just x. Okay, so y coordinate of Q, x is just equal to x. Y is equal to 10 minus x squared. And we can't replace x with x, so that's your expression for the y coordinate of Q. So the whole height from the x-axis up at the point Q is 10 minus x squared, but we know up to P is 4, so the length PQ, okay, the length PQ is equal to the whole height, which is 10 minus x squared, subtract the 4 that's underneath, so it's 6 minus x squared. Okay, which means for part 2, so 1 is that, part 2, we're looking for an expression for the area of this rectangle. Well, we know there, I'm just going to rub this out in a minute. We know here that T to P is x, so the length of that rectangle is 2x. And we know the length from P to Q is this 6 minus x squared. And then just multiply the brackets, it's 12x minus 2x cubed as required. Okay. Okay, and here's a pretty tough log question as well. Okay, so in 7a, we're told that log to the base 4 of x is equal to p, and we're asked to show that log of x to the base 16 is equal to half of p. Okay, now the problem here is we're changing base. The 4's got to change to a 16. Now, what I would do to look at this is just rearrange it into the exponential form. So from this, we know that x is equal to 4 to the power p. Okay, so there's my power there that I want to change. Now, because logs are all to do with powers, I'm going to change that into a power of 16. Now, we know that 4 in terms of 16 is the square root of 16. So x really is the square root of 16 to the power p. But we don't want it just in square roots, we want it in powers. So 16 to the power half to the power p. And then rewriting that again back into exponential means that we've got log to the base 16 of x is equal to a half p. Okay, and that's you showing that. Okay, so that'll be your 3 marks there, one for rewriting, one for subbing in the 16, and then one for converting back. Okay, I'm going to do a little bit of extra work here though, because it's going to help me with part B. So essentially what that means is log to the base 16x is equal to half of log x to the base 4. Okay, now the key relationship there is because 4 is the square root of 16. Okay, so you'll see in part B that you're looking at something very similar. You've got an equation now with 2 different bases, and this is why it's the last question in paper 2, because it's taking something extra, it's adding something on, it's changing bases. Okay, but here we know that for the squared version is half the log of the unsquared version. So this is log x to the base 3 still, but this 9, because 9 is the square of 3, this is really half log x to the base 3. Okay, it's a tough question this, and you can see why, but last question of paper this is to separate the A band 2s to the A band 1s. Okay, and now we've got an equation we can solve because the bases are the same. So it's log x to the base 3 plus log x to the base 3 of a half is equal to 12. We're adding logs now, so that's log 3 of x times x to the power half, which is x to the power 3 halves equals to 12. And then we've got a situation where we can rewrite an exponential. So x to the power 3 halves is equal to 3 to the power 12, and then it's just sums. Okay, it's not nice sums, I get big minging numbers, I have to check it actually because I thought I made a mistake, but no, I am right as always. Okay, so x, to get rid of this square in the bottom, is going to be 3 to the power 12 squared, and to get rid of the cubed, it's going to be the cubed root. Okay, so x is going to be what was the answer again? I've got it here somewhere. What the hell lost it? It's 3 to the power 8, I believe. 6561. Okay, so it's all about changing base, and this is a problem-solving question. It's showing you a relationship, and you can't, you don't have any log laws there to do. So what we can start doing is start rearranging. Okay, we want that change to that 4 to change to a 16, so we write the 4 in terms of a power of 16, and then rearrange back, and it gives us the desired relationship, and then we can use that relationship to extrapolate. And again, it's mental. It's a really tough question, just like the last one, but that's what it is. It's lovely. Actually, it is. It is lovely. Right, hope that's all right. Any more requests? Give us a shout.